Hello everyone. In this video, we are going to talk about algorithms for performing range queries using B plus trees, right? So I have two examples over here. So first, let me start with the simple case. So in the first case, we have an employee table, and in the employee table, there are several attributes, name and all that. But most importantly, we have something called as the employee ID in that table, and this employee ID is the primary key of the employee table, right? So in other words, you will not see duplicates in this particular column, right? And furthermore, we are also assuming that we have a B plus tree on the employee ID attribute of the employee table, right? So this is a sample B plus tree. Let's say, for as an instance, you can take this, and then two things to note here. So one is that in the leaf level, you will see all the employee IDs which are present in the file, right? So that is the first thing. And the second thing is that these employee IDs which appear in the leaf level of the B plus tree will always be in sorted order, right? So those are the two important things. And lastly, one another small thing is that in the tree you just store these unique key values, and at the leaf level you basically store a pointer to the actual record where this is sitting. So for example, you pick any employee ID, let's say employee ID 20, right? So in the B plus tree, at this position you will store the address, the record address of the tuple where the employee ID is 20, right? So that's how the B plus tree works, especially in case of in case where the attribute is actually a candidate key, which is now here, right? So now in a file like this, we post the following query: select star from employee where the employee ID is between 8 and 38. So let's say that this is your query, right? So now how do you actually solve this query using the B plus tree, right? So the way we do it is we take advantage of the structure of the B plus tree here to solve this efficiently. So what we do is that we search for the leftmost point in that range. So let's say 8 in this case. So we search for the 8 in this B plus tree, and then we perform the leaf scan, right? So you may recall that at the leaf level, these leaves are always interconnected with each other, right? So these connections are always there. And we also know that all the IDs which are there in the employee table, they happen to appear in the leaf level and they are in sorted order. So if we have to just get the record addresses of all the tuples whose employee ID is between 8 and 38, all we have to do is that we first reach this particular leaf where 8 is sitting, right? And then we sort of scan through the entire leaf, right? So we keep going to the next block, next until and unless we find the end of our range, right? So in this case, the end of the range is 38. So we basically take out all these record addresses from these entries, and then we will actually go to the file, go to all those corresponding record addresses and get the whole tuple, right? So this is how a B plus tree is used for solving range queries uh, on a candidate key, right? Okay, so now in the next slide, what I will do is I wanted to go over the cost expression, right? Okay, let's continue. So here, I'm making some assumptions first. So I'm assuming that I have a B plus tree on the search key. And as you know, B plus tree is a secondary index. So that means, the file is not sorted on the key attribute, or the file is not sorted on the, the attribute on which B plus tree is constructed. And so there are two cases. So one is the search key being a candidate key, and the other one being that the search is on a non-candidate key. So in the first slide, I'm going to cover the case where the search is happening on a candidate key, uh, and then we are searching for records between values x and y. So this is a typical range query, right? So as an example of this, so let's say that x and y are 100 and 200, and we want to retrieve all the records where the employee ID is greater than 100 but less than 200, right? So as I covered in the previous slide, the on the high level, the algorithm goes as follows: you search for 100 in the B plus tree first, and then perform a leaf scan to get all the records containing the EIDs between 100 and 200, right? And in actual thing, the way it will happen is that you start the leaf scan from 100, and then you basically stop when you reach 200, because we know that in the leaf level of the B plus tree, all the entries are always sorted, right? So once you reach 200, you don't need to go beyond that. Okay, so that's how it goes. And now, how what is the total cost of doing this operation, right? So now we'll get an estimate on that, right? So there are so two or three major steps over here, right? So you may recall that in the first step, what we do is that we search for the left side of the range, right? So in this case, we searched for 8, right? So in this particular case, we search for 100 in that B plus tree, right? So for searching that leftmost point of the range, we are going to traverse the B plus tree from root to leaf, and for doing that we will access some height number of disk blocks, right? Because you may recall that each of these nodes of the B plus tree is actually one disk block, right? So for reaching from root to leaf, for searching 100, we are going to access height number of disk blocks, right? So now after you reach the leaf level, you have to perform the leaf scan until and unless you reach the tail end of your range, right? So for doing this, what I'm saying here is that I'm going to access some SB divided by blocking factor of leaf number of disk blocks. So, and let me give details what it is. So here SB is the expected number of unique values between x and y, right? So recall that your employee IDs may not always be 100, all the way up to 200. Some numbers may be missing, right? Obviously one thing is clear, that you will not see a repetition of employee IDs because this is a candidate key, but nevertheless some integers between 100 and 200 may be missing. So you need to get an estimate of the number of employee IDs which will actually come in the range of 100 and 200, right? So let's say that SB is that expected number of employee IDs which will fall within this range. In the actual database, in real world, the way your database will do it is that your database actually maintains an histogram on all column attributes. Especially, it will maintain a histogram on at least all the primary key and all that, right? It may maintain those histograms on other attributes also, right? So using that histogram, your database engine will actually estimate this value as B, right? So from that histogram, it will estimate that given 100 and 200, it will get a very rough estimate on how many unique values will it actually catch. Maybe slightly off, but ballpark it will be okay, right? And now those many number of unique values will be read at the leaf level, right? Now in the leaf level, uh, we know that uh, we know that in each level, in each leaf node, we have only some number of those IDs, on some number of record addresses, right? And this is and this number of pointers which can be stored in one leaf node is determined by the blocking factor of the leaf of this B plus tree, right? So that is this parameter BFR leaf. So BFR leaf is the blocking factor of the B plus tree, right? So the number of tuples which can be stored in one node of the B plus tree, right? Now I need SB number of tuples because I have estimated that between 100 and 200 I will get SB number of unique tuples, right? And then in each node I can store BFR leaf number of tuples, right? So if I have to read SB number of tuples, I will be reading SB divided by BFR leaf ceiling of that, right? Of course, this number may be slightly off, because what may happen is that let's say if your SB was actually 4, right? So as per the blocking factor of this particular B plus tree, you will compute that all these four tuples will fall in just one node. But in reality, if your range is like 22 to 29, right? So you will be reading two disk blocks, right? So the formula might be slightly off, but nevertheless it will always be in the ballpark, right? And this is very typical in database systems, right? We don't care to get the precise estimate, because even getting that precise estimate will take a lot of time, and then performance and runtime is really what matters the most. So on an average it should be okay, right? Okay, so coming back here, so I said that the cost of reading all the record addresses for the employee IDs which fall between 100 and 200 will be this quantity, where the numerator is the expected number of unique values which fall between x and y. You divide it by the blocking factor of the leaf of B plus tree, and then you take a ceiling of that. Okay, so this is the number of disk blocks, estimated number of disk blocks that you are going to read on the leaf level, right? So now the total cost, we are ready to put the expression for the total cost of the range query algorithm on B plus tree, right? So the total cost will have three things. So the first part is, as you recall, you have to access root till leaf for searching the leftmost point in the range, so that height number of disk blocks will be taken. And then you have to do a leaf scan for getting the addresses of all the records whose EIDs is between 100 and 200, and we do this by performing a scan on the leaf level of the B plus tree, right? So this is the number of disk blocks that will be consumed for doing that part. And then finally, last but not the least, remember that you got SB number of record addresses, and those all these record addresses are the addresses of the tuples whose employee ID is between 100 and 200. So now you have to actually go to that tuple and then fetch that record as well, right? So this last SB is for that part, right? So this is the part where you actually go to each of these record addresses, SB number of record addresses, and get the actual tuple, right? Because remember, your query was select star from employee, so you need to get all the details of that tuple, not just employee ID, right? If I had written just select EID from employee where EID is between 8 and 38, then perhaps this may not have been needed, because you don't need to actually go to the file. But here, since I have written select star, you actually need to go to the file and retrieve the entire tuple out. So this SB will be extra, right? So this is the total expression of this is the total expression of the number of disk blocks that you will access for solving a query, something like this, where your search attribute is a candidate key, and then you have a B plus tree on that candidate key, right? So, and note that as I told before, that so this is just an estimate. This may be off by 1 or 2 blocks. The example which I gave is that if your SB value was 4, yeah, your formula will say that you will have to read only one disk block at the leaf level. But if your range was something like 22 to 29, then you will end up actually reading two disk blocks, right? So for those reasons, this expression may be off by 1 or 2 blocks, but more or less this will still be on the right ballpark, right? So now you can ask this question, right? Okay, so this is the expression of range query solving, range query solved by using B plus tree, right? So you can ask this question, when is this going to be used? Remember, the way database will think is the following, right? So you give a query like this, select star from EMP where employee ID is between 8 and 38. So what it will do is that it always has two options, right? So one is, of course, you use the B plus tree and then, retrieve all those relevant records. Or second approach is the naive approach. In the naive approach, what it will do is that it will just straight away go through the entire file tuple by tuple, and for each tuple it will check whether the employee ID is between 100 or 200 or not, right? So that is the naive approach, like a linear scan, right? So now the question for the query optimizer is always the following. For range queries, should it access the B plus tree, or should it do the linear scan of the entire file and return, right? So you can say that, why not always use the B plus tree? It is not always B plus using range queries on B plus tree is not always efficient, and I'll tell you the case where things start to get interesting. So if it happens that, for example, consider a case where this SB number happens to be very high for you. So for example, if you estimate that, the range which I have given in the range query, it is such that approximately 98% or 95% of the tuples will match that range. So if the range is very wide, then what will happen is that, this number, along with this height and seal, this number becomes a very big number, because remember, you are doing one disk block for every record which is between X and Y, right? So if this XB is large, then, then this whole expression will become very high. Instead, in such a case, what the query optimizer will do is that, it will just, give up on the B plus tree. It will just do a linear scan. So that is the sort of dominant zone which your query optimizer plays. So typically, the thing that you should remember is that if the range is narrow, right, which means that means, if the SB value is small as per the estimate, then the query optimizer will typically choose the B plus tree if it is available. If there is no index available, then, there is nothing you can do about it. But if an B plus tree index is available on the search key, and the SB, which is the estimated number of values which will hit in the range, if that value comes out to be small, then, then this expression will be lower. In that case, the query optimizer will actually use a B plus tree to solve the range query. On the other hand, if the SB value turns out to be very high, it's like, maybe 90% or 95% of the records hit that range, then, it's better to just drop the B plus tree and do a simple file scan, you know, because, that itself is going to come out to be less, because remember, you are going to read the file block by block, right? So here, instead of doing SB number of disk accesses, that number will come small, because, you're going to read the file one block at a time. Not You will not be doing a random IO for every record. You will be doing a random IO only once per block of the file, right? So that comes out to be smaller, but for that SB needs to be very large in number. Okay, so that is sort of the moral that you should remember here. Okay. Okay, now we are going to cover the case where the B plus tree is built on an attribute which is not a candidate key. Right? So let's take this example. So let's start from employee table where department ID is between 8 and 38. So clearly, department ID cannot be a primary key of the employee table. Just from the semantics, I'm taking this example, right? So department ID again is an integer, and then let's say that, you have a B plus tree on the department ID column of the employee table, right? And as I said, we can expect to have duplicates in the department ID column of an employee table, right? So now when we construct a B plus tree on a column which is not a candidate key of the employee table, so the way we go is that, in the tree by itself, we'll have only the unique values of the department IDs, right? However, the key contrast being that, at the leaf level, in case of a candidate key, so this was simply pointing to the record this just stored the address of the record where this particular employee ID was stored, right? So that was how we did previously. So now in case of department ID, which is a non-candidate key, in other words, you can have duplicates in that particular column. The way we store it is that, at the leaf level, we will store a pointer to a disk page which will actually contain the list of record addresses where that value appears, right? So this is an example of that. So for example, you pick up department ID number 39, right? So at the leaf level, this tuple will store 39, which is the key value, and also it will store an address of a disk page which will contain all the record addresses where department ID number 39 appears in the employee table, right? So this is how the B plus tree is constructed on an non-candidate key column, right? So I think I may have mentioned this before also. Whenever I say that we have a B plus tree on a non-candidate key, we will always assume that the B plus tree by itself will contain only the unique values of that column. But at the leaf level, instead of directly pointing it to the record address where those values appear, it will point to an indirect page, which will contain all the record addresses where the that particular department ID or whatever column that you're interested in, that value appears, right? So in this case, with each of these entries, I'll store an address to a disk page where I will store all the record addresses where that particular department ID appears, right? So this is just an example of that over here. Okay, so now in a case like this, now if you want to run this query using B plus tree, so what you will do is that, similar to before, you will always search the leftmost part of that range, right? Actually, you can search this part also and traverse in the reverse direction, but that's okay. Cost wise, it doesn't really differ much. It's the same logic. So you search for one end of the range in the B plus tree, and then you perform a leaf scan until unless you hit the other end of the range, right? And while you are traversing them, you get all these addresses where those department IDs actually are stored, right? So now let's try to see if we can develop an expression for this cost, right? So the setting is same, right? You have the B plus tree on you have a B plus tree on the search attribute, and the search attribute is a non-key attribute, right? In other words, you can have duplicates in that column. Okay, right? So the first step remains the same, right? We still have to search for the left end of the range in the B plus tree, right? So and the total cost for that will be height, right? So you have to traverse a root till leaf path, right? So height number of disk blocks will be accessed over there, and then you have sort of 3 steps after this. So step number 1 is that you do the leaf scan from 8 to 38 in this case, and then you get the addresses of all the indirect pages, so all these extra pages that I was talking about. So you have to get that, right? And it may also happen that it may also happen that so this indirect page, let's say department number 39 is a very big department, and then that department ID appears multiple times in the file. So all those record addresses may not be able to fit in one disk page, right? So there can be further disk pages which are chained to this one, right? But nevertheless, the after I reach from root till leaf, the first thing I have to do is that I have to do this leaf scan, right? To at least get the address of the first indirect page, right? So you have to do this leaf scan, and that part was there in previously also. So the cost of doing that leaf scan will be as I said before, ceiling of SB by BFR of the leaf. So SB is the expected number of unique values which will appear between 100 and 200, right? So if your department ID range is maybe 100 to 200, so USB is the expected number of unique department IDs which will fall within this range. Now, so each of those department IDs can itself have multiple instances in the file, but what is the unique number of department IDs which will appear between X and Y? So that value is SB. Okay, and you divided it by the blocking factor of the B plus tree. So, and you take a seal of that. So that this part we covered previously also. This is the cost of doing that leaf scan, right? So the first two parts, it's sort of coming from the previous case. So root till leaf, disk blocks accessed, and then a cost of doing this leaf scan. And now next two things, right? So how many of these indirect pages would you be accessing, right? As I said before, each of these department ID can have one indirect page or it can have multiple indirect pages, right? Because if a department ID is popular, you can have multiple of these pages lined up one after one another as a linked list, right? So the cost of reading all those indirect pages is given by this expression, right? So over here, so the two new terms are added in. So SA, I'm saying is that, it's the maximum number of records matched for a unique value of the search attribute. So that means, in our case, in case of department B plus tree on the department ID, SA is the maximum number of faculty that sit in a department. So that is the SA, right? And BFR in is the blocking factor of the pages which store these record addresses, right? Remember that, as I said, these are actually record addresses where this department ID appears, right? So SA is the maximum number, and then you divided it by the blocking factor of the indirect pages, right? So now, in our case, so let's say that let's say that each department can have at most maybe 10 employees, right? And then this BFR in happens to be maybe 20, right? So in that case, what will happen is that for each department ID, you will have only one indirect page which will contain those record addresses. Okay, so this term will turn out to be 1, and then you multiply it by SB, which is the expected number of unique values, right? So then, as expected, what is happening is that if the number of, if each department can have only maybe 10 employees, but in one indirect page, I can store 20 record addresses, then the total number of indirect pages which I will be reading will be just SB. It will be basically one indirect page per unique value of the department ID. If if on the other hand, let's say the max number of records matched for any unique values, maybe let's say 20 or 30, whereas I can store only maybe 10 record addresses. So then for each department ID, I can have multiple. I can have for each department ID, I'll have multiple pages like this. So first page will store maybe BFR in number of record addresses, and then I will chain it to store the next BFR in number of record addresses, and so on, right? So this expression sort of takes care of the total number of indirect pages that you're going to read. Okay, so that is this part. And last but not the least, so this term is the actual number of uh, you know records that you are actually going to pull out from the file. Remember that SB is the number of unique values, and SA is the max number of records that will be matched for each unique value. So the total number of tuples which will actually be retrieved from the file will be SB into SA. And given that this is going to be a random access on the disk, you have to do one disk IO for every each and every record address, right? Of course, there's a lot of assumptions in this particular expression. So for example, I'm assuming that SA is the max number of records, right? So let's say one department has maybe 100 employees, whereas the other department has only 10 employees, right? So this number will vary across departments, right? Nevertheless, this is how the databases people, they like to get the rough estimate, right? And as I said before, your database engine actually will estimate this SB out of the histogram. It will store always the histogram, and these blocking factors can always be stored in the database, right? So all of these things are stored in something called as the data dictionary of a database, and you can actually query the data dictionary also. So there are specific tables, and if you run SQL queries, it will actually throw out all these values which it stores. And, it actually stores quite a bit of metadata on top of tables, right? So in that metadata table, it will store all these things. Okay, and essay and all that, these can be as needed, they can be estimated. So so this is a rough approximate estimated number of disk blocks that you will be accessing for doing range query on a non-key attribute using B plus trees, and similar to the previous case, you can ask me, when is this going to be used? Is this going to be valuable or not? So, my answer will still remain the same. It all depends on, what is this number SB, right? So if this number and SB and SA, if this number happens to be very large, then the whole of this cost will really jack up, right? So if in such a case, what the DB engine will do is that it will just drop the B plus tree. It will simply do an linear scan of the file, right? Because as I said before, also this term, you are doing a random IO for every tuple which is matching, right? Whereas if you had actually done a linear scan, you will be doing a random IO only for one disk block amount of data, okay, or one disk block amount of employee records. Okay, so that is the advantage, right? So typically, these kind of things are used when the ranges are small, right? So the database engine will actually estimate these things on the fly and then decide whether to do linear scan or whether to do B plus trees, right? In your database, actually, you can see how it is working. There's something called as, explain plan command. It's almost all databases have that. So if you give it a query and you throw it in the explain plan command, it will actually show you what the query optimizer decided. Did it go for B plus tree followed by scan, or did it go for linear? You can actually see these things on the fly, right? So maybe you'll do that as a part of a different course. Okay. Okay, good. So that was all about range queries on B plus trees. Okay. So as I say multiple times, in the previous video also said, do not mug up anything, and do not try to mug up this expression, right? So these expressions, they are very intuitive in nature, and you can construct them on the fly. There is no black magic going on anywhere, right? There is a meaning for all of these things. They can be off by few blocks, these expressions, because a lot of assumptions are going in, right? For example, in this expression, I am assuming that each department has SA number of records. I mean, that may not be true, but and then it may be then non-trivial to even estimate SA for each and every department ID. That will be just like too much. If the information is there, fine. Otherwise you have to approximate, right? So these expressions, they will be off by few blocks, but as long as they are conceptually okay and they are in the same ballpark, it's all looks good. Okay. Okay then. So I'll stop this lecture now. Thank you.